Greetings class, Mr. S here again. Today we are going to introduce a new unit, Unit 7. Unit 7 is called Chemical Quantities. Our last unit was Chemical Composition and the Mole. This chapter is going to be called Chemical Quantities. Now, just before we start the lecture notes on the mole ratio, which is a key concept in chemical quantities, let's just talk a little bit about what this chapter is going to be like. Well, in this chapter, what we're going to do is we're going to merge the last two units. The unit on writing and balancing chemical equations with these coefficients here. And we're going to merge that together with moles and the stuff that we learned in the mole conversion chapter and the chemical composition chapter. And the type of question we're going to be able to answer at the end of this unit is this. So let's say that you owned a company and your company made chlorine gas for sale. This is your business. And you had an order for 100 liters of chlorine gas. Okay? Now you might want to know, well, how much HCl do I need to start off with in order to get my 100 liters? How much MnO2 do I need to start off with to make my 100 liters? Now, you might say, well, if I put about 500 of these and, 400 liters of this, wouldn't I for sure get 100 liters of chlorine? You might, and you might not. And if you would, well, then that might be wasteful. Wouldn't it be prudent to know just how much MnO2 and how much HCl you need to start with to make exactly 100 liters of chlorine? So now that I've given that little introduction into the type of problem we're going to be solving, that is, how much of a product can I make from a certain amount of starting material? Okay, one of the absolute #1 key concepts in this chapter, something that we're going to use in every single problem pretty much in this chapter, is something called the mole ratio. And so what I like to do is start this out in the introductory section here, making sure that we all understand what the mole ratio is, what it does, what it can do for us, okay? And then pretty much by the end of this this introductory lecture, we're going to be using the mole ratio to do some of these product amount predictions. So it's a key concept, but luckily it's not a very hard concept to learn. Okay, so let's kind of go back to the chemical reactions chapter, where we learned that in the balanced equation, that's what BEQ stands for, these coefficients, and there's a 1 and a 1 and a 1, these coefficients tell you the numbers of atoms or molecules, or we also said the number of moles of each participant. Remember, participant means either reactant or product. It's a way of lumping them all together in one word. The coefficients tell the number of atoms, molecules, but also the number of moles of each participant in the chemical reactions. Now, what's different, a little different about how we're going to write them in this chapter, we're going to write them as a ratio. So if you had to write the ratio of the molecules in this chemical reaction, you'd see, well, there's 1 mole of MnO2 for every 4 moles of HCl. And what that's going to do is produce 1 mole of MnCl2, 2 moles of water, and 1 mole of chlorine gas. So as you guys can see, I took that balanced equation, and what I did was I basically just took the coefficients out, but instead of just writing 1, 4, 1, 2, 1, I wrote them as a ratio. And again, since these coefficients represent the number of moles, and I'm writing them as a ratio, voila, the mole ratio. Oui, oui. Okay, now let's see if we can use this concept of the mole ratio to answer a few questions here about this chemical reaction. So how many moles of MnO2 and HCl participate in this balanced equation? Well, that's not too hard. We just kind of figured out that there is 1 mole of MnO2 and there are 4 moles of HCl. And again, that's because of these coefficients. All right, question number 2. How many grams of MnO2 and HCl participate in the balanced equation? Well, we don't know the number of grams, but we know the number of moles, and then, so we can go from moles to mass using the molar mass. So let's set that up. Okay, so let's use the molar mass, as I said. So it turns out the molar mass of MnO2, if you add up one Mn and two O's, is 86.937 grams of MnO2 in 1 mole of MnO2. For HCl, the molar mass, if you add up one H and one Cl, 36.461 grams of HCl. Whoops, I put that in the denominator. Wrong. 36.461 grams of HCl in 1 mole of HCl. Sorry about that mistake. When you do the math, you see that you would have in this reaction 86.937 grams of MnO2, and you would have 4 moles of HCl, which would be 145.844 grams of HCl. So basically what we saw there was we just used the molar mass to go from moles to mass. All right, guys, let's move on to question 3. So how many moles and grams of Cl2 would be produced in this case? Well, 1 mole of Cl2. How many grams would that be? Again, we're going to multiply by the molar mass of Cl2. Add 2 chlorines together, and the molar mass would be 70.906 grams of chlorine per 1 mole of chlorine. And you would see that we would make it, the way this chemical reaction is written, we would make 70.906 grams of chlorine. So you see, guys, how we just use this mole ratio to determine the amount of chlorine we could make. Now, finally, let's tackle this last question, but I'm going to scroll it back up so we can see the balanced reaction. What if you wanted to make 10 moles of Cl2? Here you're making 1 mole. But what if we wanted to make 10? Well, if you think about these guys as a ratio, and in the original equation, it was 1 mole of MnO2 for every 4 moles of HCl. And with that, you would make 1 mole of Cl2. Well, then to make 10 moles of Cl2, wouldn't you have to start out with 10 times as much? That is 10 moles of MnO2 and 40 moles of HCl. And then you would make the 10 moles of Cl2. How many grams would that be? Well, 10 moles of Cl2 times the 70.906 grams per mole of Cl2. So in that 10 moles of Cl2, we would have 709.06 grams. You see that? That's 10 moles times the molar mass. So as I mentioned a few minutes ago when I was introducing what this chapter would allow us to do, we said that we were going to be able to use this mole ratio that we were going to learn about to predict the amount of product that we might make under certain conditions. Okay? Gentlemen, we just did something called stoichiometry. Stoichiometry. Oh, Gesundheit. God bless you. Now, stoichiometry is actually another name for chemical quantities. All right, it's a Greek-rooted word, the metri meaning measurement, and stoichio has something to do with amounts or elements or something like that. So stoichiometry has something to do with predicting the amount of compound that we would make. And so what is stoichiometry? Well, you just saw it in action, but let's write a definition of stoichiometry. Well, it's using the relationship between those participants in a balanced equation the coefficients that is, to predict the amount of participants. As you saw, we predicted the amount of chlorine gas we would make, okay? And so what's that relationship? What is this relationship? Well, that relationship, as we saw, were the coefficients, but when we wrote them as a ratio. And so what we're going to say is this relationship that we're going to use anytime we do stoichiometry, anytime we try to predict chemical quantities, right? We're going to use that mole ratio. Again, that mole ratio is simply the ratio of the coefficients in the balanced equation. Okay, now that we've defined what stoichiometry is, just using the relationship between participants to predict the amounts of participants, and we know that that relationship is the mole ratio, let's practice writing the mole ratio between different participants in a balanced equation. So I have 4 questions here. What is the mole ratio of MnO2 to MnCl2? And for that mole ratio, we're going to look to the coefficients. The coefficient on MnO2 is 1, and the coefficient on MnCl2 is 1. So I would say that my mole ratio is 1 mole of MnO2 to 1 mole of Cl2. MnCl2. Also, you guys know you can write a ratio this way with the colon, but another way we write ratios is sort of as a fraction, and so you could also write this like this: 1 mole of MnO2 for every 1 mole of MnCl2. Okay, so we're going to even though the mole ratio written strictly as a ratio looks like this, it turns out, guys, that when we use these in a problem, you'll see in the next lecture that when we use them in a problem, we're going to more use them sort of like written that kind of this way as a ratio. Okay, let's do the next one. What is the ratio of MnCl2 to Cl2? Well, again, I'm going to look at the coefficients. 1 mole MnCl2 to 1 mole of Cl2, or written as a ratio this way. Okay. How about HCl to Cl2? Well, there are 4 moles of HCl to 1 mole of Cl2. And the last one, there are 2 moles of H2O for every 4 moles of HCl. Let's go ahead and write those as a ratio, like a fractional ratio. Okay, there you go. I filled them in. Now, you notice that this ratio here has a multiple in it, and you might be tempted to reduce that ratio to 1 to 2. But as what we're going to see as we go through this stoichiometry chapter is it's best just to leave that ratio written the way it is. And so we won't reduce that ratio, even though we might be tempted to. Okay? All right, guys, let's do 2 little practice stoich problems, some simple stoich problems to end this little introduction to stoichiometry. Well, in that example I gave in the on the very first page of notes, where I said what would we need to start with? How much MnO2 and HCl would we need to start with to make 10 moles of Cl2? Well, 10 moles of Cl2 was a nice round number, and it was really easy to go, if there's 10 of these, there has to be 40 of these and 10 of these. But what if the amount that you are asking about is not a nice whole number like 10 mole, 1 mole, 2 mole? What if it's something oddball like 0.736 moles? Okay, and you want to know, to make 0.736 moles of water, okay, how much HCl, or how many moles of HCl would you have to start with? So let's see how we might set this up using the mole ratio. before we proceed here in a second, let's just kind of think of what we want to do here. We kind of want to turn the amount of water, this amount of water we want to make, and we kind of want to relate that to the amount of HCl. And even though this really isn't a conversion per se, what we're really trying to do is relate two amounts. And in a way, we're going to be able to set this up kind of like a conversion. And so you'll see when I go to start this problem, I'm going to start it off with my factor label method, with my picket fence. And so thinking of this sort of not really a conversion, but kind of a conversion, let's always start with what we're given. And so here's what we know. We know that we have 0.736 moles of water. And what we want to do is kind of turn that into moles of HCl. Now, one way we can do this is we use our mole ratio, and we can think, well, you know, there's going to be 4 HCl for every 2 moles of water. And so what we can do is kind of write that mole ratio 4 to 2. We can kind of write it as a conversion factor. So check this out, check this out, check this out. Okay, I'm going to write it in here as a conversion factor. What I'm going to say is for every 4 moles of HCl in my balanced equation, I have 2 moles of water. Okay, for every 4 moles of HCl, I have 2 moles of water. And you can see those, that's my mole ratio from the balanced equation. And lo and behold, when I do that though, look, moles of water in a sense cancel out. Okay, it's pretty amazing. And so then what you're going to see is, well, what if to find out the number of moles of HCl, I'm just going to have to multiply 0.736 times 4 and divide that by 2. So let's do that. All right, let's go. So it turns out that is 1.472 moles of HCl, because that moles of HCl is really the unit that's kind of left over when I kind of apply this mole ratio to this problem. Let's also look at sig figs. My starting amount has 3 sig figs. These guys are whole numbers, and so those are unlimited. And then this is going to have to be rounded to 3 sig figs. And so the best I can do in this problem, although I'm not really going to worry about 2 sig figs too much at this point, we're just trying to learn the method. It turns out we would need to start with 1.47 moles of HCl, because how many moles of HCl would we need to make this much water? And that's the answer, guys. Okay, let's do one more problem to wrap this up. How many moles of aluminum oxide would be made if in this new reaction, it's a brand new balanced equation, if I started out with 0.882 moles of oxygen? Okay, and so there's my, again, modeling for you the way I set up that first problem. I know I have 0.822 moles of oxygen, and I want to know how many, that's why I put the question mark there, how many moles of aluminum oxide would be made. Okay, so there I started it out just like I did the last one. Made another mistake. You know, I'm the king of mistakes. Okay, 0.882 moles of oxygen. And I'm going to do that same mole ratio thing, because what I can see from my balanced equation is that there are 2 moles of aluminum oxide for every 3 moles of oxygen in the balanced equation, because this is the relationship that's going to allow me to calculate these amounts. That's stoichiometry. Okay, and then when I do that, I get, do the math, 0.822 times 2 divided by 3, because it's in the denominator, and I get 0.588 moles of aluminum oxide, and that's how much I would make. Now, what I can do is extend this. And the way I'm going to extend it is, once I know the moles of Al2O3, I might want to know, well, how many grams of Al2O3 would be made? Well, we all know from last chapter that we can take this mole amount right here that we got from the first part of this stoich problem, and multiply it by the molar mass of Al2O3, and we'd be able to get grams. Well, the molar mass of Al2O3, 2 aluminums, 1 oxygen, is 101.960 grams of Al2O3 per 1 mole of Al2O3. When I complete the math, I get 59.9 grams of Al2O3. Check that out. So what we did was we started out with the number of moles of oxygen that we knew. From that moles of oxygen, we calculated using our mole ratio, we calculated the moles of Al2O3 we would make in this reaction if we started out with that amount. But then if we didn't want to know the number of moles, if we wanted to know the number of grams, well, you just have to multiply this mole number by its molar mass to get grams. Finally, and you can kind of see what's coming in some future lectures on stoichiometry, is what if we wanted to know the number of particles of aluminum oxide that were in this? Well, moles to particles, Avogadro. Okay? And so you see stoichiometry, because it's all based on the mole and this mole ratio, you're going to be able to calculate the number of moles of product. You're going to be able to calculate the number of grams of a product you could make. And if you use Avogadro, you'll be able to figure out the number of particles. Let me tell you what, stoichiometry, man, it's it. All right, signing off now. Be ready for more Stoic in part 2 of the mole ratio and stoichiometry.